SIP, Session Initialization Protocol. The Session Initiation Protocol, SIP, is a text-based signaling protocol used to initiate, maintain, and terminate real-time sessions that include voice, video, and messaging applications. It is the industry standard for Voice over IP, VoIP, and has largely replaced traditional TDM signaling, like CA and CCS, in modern networks. How SIP works. SIP is an application layer protocol that operates independently of the underlying transport layer. It can run over UDP, TCP, or TLS. It follows a client-server architecture similar to HTTP. Signaling versus media. SIP does not carry the actual voice data. It only handles the signaling, ringing, hanging up, etc. Once a call is established, a separate protocol, usually Real-Time Transport Protocol, RTP, is used to stream the voice packets directly between devices. SIP addresses. Users are identified by a SIP URI, which looks like an email address, example sipuser@domain.com. The core SIP architecture. A SIP network consists of several key components: user agents, UA the endpoints. This includes UA clients, UAC, that initiate requests, like a VoIP phone, and UA servers, UAS, that receive them. Proxy server, an intermediary that routes SIP requests to the user's current location. Registrar server, a server that accepts register requests, keeping track of where users are located on the network. Redirect server, informs the client of the next hop the call should take, rather than routing the call itself. SIP message examples. SIP uses readable text commands. Common methods include: invite, initiates a call session. ACK, confirms that the client has received a final response to an invite. BY, terminates an established session. Register, tells the SIP server the user's current IP address. Integration with SDP. To negotiate call details, like which voice codec to use, SIP carries a payload called Session Description Protocol, SDP. SDP defines the technical parameters of the media stream, such as port numbers and encryption keys. Signal flow of SIP between UAC and UAS. The signal flow between a user agent client, UAC, and a user agent server, UAS, follows a standardized sequence of requests and responses to establish, manage, and terminate a voice session. SIP call flow diagram, UAC to UAS. The following diagram illustrates the three-way handshake used for call setup, followed by the media exchange and session termination. Signal flow steps 1. Invite, UAC rightward arrow UAS. The UAC initiates the call by sending an invite request containing the session parameters, via SDP. 100 trying, UAS rightward arrow UAC an optional provisional response indicating the UAS has received the invite and is processing it. 180 ringing, UAS rightward arrow UAC a provisional response indicating the destination device is alerting the user, the phone is ringing. 200 OK, UAS rightward arrow UAC a final success response indicating the user has answered the call. 5 ACK, UAC rightward arrow UAS the UAC confirms receipt of the 200 OK. This completes the three-way handshake, and the call is now established. 6 RTP media, peer-to-peer. Once the handshake is complete, voice data flows directly between the UAC and UAS using the Real-Time Transport Protocol, RTP. 7 BY, either side to end the call, one party sends a BY request. 200 OK, receiver rightward arrow sender the other party acknowledges the termination with a final 200 OK. Key concepts: transaction, a single request, like invite, and all its associated responses, like 100, 180, and 200. Dialogue, a peer-to-peer relationship between two user agents that persists for the duration of the call, identified by the call ID and tags. Role change, in a typical VoIP session, a phone acts as a UAC when placing a call and as a UAS when receiving one. 5 Why SIP replaced CA/CCS compared to the TDM-based signaling discussed previously. SIP offers significant advantages: flexibility, it can handle video, file sharing, and presence, status, information, not just voice. Scalability, since it is software-based and runs over standard IP networks, it is easier and cheaper to scale than physical T1/U1 hardware. Interoperability, it provides a universal standard for different vendors to communicate. For more technical details on the standard, refer to RFC 3261, the primary specification for SIP. 6 Modern use cases. SIP trunking, replacing traditional T1/PRI lines to connect a business's PBX to the Internet. VoLTE, Voice over LTE. Mobile carriers use SIP to deliver voice calls over 4G and 5G data networks. Unified communications, powering platforms like Microsoft Teams and Zoom. RTP, Real-Time Transport Protocol, while SIP handles the signaling, the handshake, the Real-Time Transport Protocol, RTP, is the workhorse that actually carries the digitized voice and video data across the network. It is designed for end-to-end, real-time delivery of interactive media. Defined in RFC 3550, RTP typically runs over UDP to minimize overhead and latency, as retransmitting lost voice packets, which TCP does, would cause unacceptable delays in a conversation. The RTP header fields. An RTP header is at least 12 bytes long and contains critical information to help the receiving device reassemble the audio in the correct order and at the right speed. Size field description, bits, version, v2 identifies the version of RTP. The current version is 2. Padding, p1 if set, indicates there are extra padding bytes at the end of the packet. Extension, x1 if set, indicates the fixed header is followed by exactly one header extension. CSRC count 4 indicates the number of CSRC identifiers that follow the fixed header, used in mixers. CC, marker, M1 used at the application level to mark significant events, such as the start of a talkspurt in voice. Payload type 7 identifies the format of the payload, example G.711 PCMU is type 0, G.729 is type 18. PT, sequence 16 increments by 1 for each packet sent. It allows the receiver to detect packet loss and restore packet order. Number reflects the sampling instant of the first octet in the packet. It is used to calculate jitter and ensure timestamp 32 synchronized playback. Synchronization source identifier. A unique ID that identifies the specific source of the stream within a SSRC32 session. 0 to 15 contributing source identifiers. Used only if multiple sources have been mixed into one stream, example a CSRC list items conference bridge. Key functions of RTP1. Sequence numbering. In IP networks, packets can arrive out of order. The sequence number allows the receiver to put them back in the correct sequence. 2. Time reconstruction. Timestamping. RTP provides the timing information necessary to play back the audio at the same rate it was sampled, helping to smooth out jitter, variations in packet arrival time. 3. Payload identification. The payload type field tells the receiver which codec, like Opus or G.722, was used so it knows how to decode the audio. 4. Companion protocol. RTCP. RTP works alongside the RTP control protocol, RTCP, which provides feedback on the quality of the service, loss rate, round-trip time, but does not carry media itself. RTP versus SIP. In the signal flow. To relate this to your previous question, the SIP 200 OK message contains the RTP port and codec in its SDP, session description protocol, body. Once the UAC and UAS agree on these, they stop talking SIP and start sending RTP packets directly to each other using those agreed upon header parameters. Protocol type, PT. In RTP header, the payload type, PT, field in the RTP header is a 7-bit identifier that tells the receiving device which codec or format is used for the audio or video data. Because it is 7 bits, the values range from 0 to 127. These are managed by IANA, Internet Assigned Numbers Authority. They are divided into 2 categories, static, fixed assignments, and dynamic, assigned during call setup. 1. Static payload types, common values. Historically, many codes were permanently assigned. While modern implementations prefer dynamic negotiation, these static values remain standard for many legacy systems. PT value encoding name media type clock rate, Hertz, description 0 PCMU, G.711, audio 8000 standard North American PCM, MULA, 3 GSM audio 8000 early mobile voice standard 4 G723 audio 8000 low bitrate speech codec 8 PCMA, G.711, audio 8000 standard international PCM, ALA, 9 G722 audio 16000 high quality wideband audio 13 comfort noise audio 8000 silence suppression background noise 18 G729 audio 8000 high compression voice, 8 kbps, 26 JPEG video 90000 still image / video frame 31 H261. Video 90000 early video conferencing standard 34 H263 video 90000 standard video for early VoIP. 2 dynamic payload types, 96 to 127, modern codecs and special formats, like DTMF tones via RFC 2833 or the high-fidelity Opus codec, do not have fixed PT numbers. Instead, they use the range 96 to 127. How they work: the SIP session description protocol, SDP, negotiation assigns these numbers on a per-call basis. Example, one call might use PT 101 for telephone events, DTMF, while another uses PT 98. Common dynamic mappings, 96 to 127, used for H.264 video, H.265, HEVC, Opus, and AMRWB. 101, frequently mapped by default in many systems for telephone event, touch tones. 3 reserved and unassigned ranges. 1, reserved, formerly 1016 audio, 2, reserved, formerly G721 or G72632, 19, reserved, formerly CN for G.729, 20 to 24, unassigned 35 to 71, unassigned, reserved for RTCP conflict avoidance, 72 to 76, reserved for RTCP packet type 77 to 95, unassigned for the absolute most current list of every assignment, refer to the IANA RTP payload types registry.